Hi, I'm Dan Abel, and in this video we'll be drawing force vectors acting on a point charge placed in an electric field. A few things we need to keep in mind when drawing our force vectors. So if this is our electric field, let's say it's curved, and we want to draw the force at this point. Let's call this point P. Now the electric field, as we talked about earlier, points in the direction that a positive charge would experience a force. So the force vector itself will always be tangent to that field. So at that point P, the tangent line just touches the electric field line at that point, and we've got our force vector. So the force is always tangent to the electric field at the point you're looking at. And just like back when you in first semester learned about forces, longer arrows indicate a greater force. And then remembering that physicists are always positive people, if the charge you place at point P is positive, we will be with the field. If the charge you put at point P is negative, we'll be against the field. Let's take a look at a question to help drive this home. So here we want to draw some force vectors acting at points A, B, and C. And we need to consider both direction and length, magnitude. So looking at A, B, and C, because A is closest to the charge, it should experience the greatest force if we put a test charge there. B is the farthest, it should experience the least force. And then the field for a single charge is just radiating outwards. So this tells us that all of these forces that we draw should be tangent to this field or pointing radially outwards. So whatever length we draw A, that's going to be our biggest. So C needs to be a little bit smaller than that. And then B is the farthest away, so it's the lowest force. So it needs to be even smaller. And we'll go ahead and label these FA, FB, and FC. So we have a little bit more complicated field here, one that's created by two charges, and you'll learn in the next lesson how to draw this field. But for now, we have the same question to draw the force vector acting on a positive 1 coulomb charge at each of the locations. So we still need to look at the magnitude of the force that'll decide our arrow length, and then we need to make our arrows tangent to the field. And since these are positive charges, they're going to point in the same direction as the field. So as I look at these 3 points, I need to decide who's going to have the greatest force. And to do that, I look at where the lines are closest together. And that is point A. Point A has the largest field density. So it'll get our longest force vector, and it'll be pointed straight at the negative charge along the direction of the field. So this will be force of A. And then B and C, C is in a slightly more dense region, but they look to have about the same density of field lines, and so they'll get roughly the same length of arrow. And again, these should be tangent, so these should be straight arrows that are tangent uh, to the path at that point. And so if we draw fairly carefully, this arrow should be slightly below horizontal for the force of B and a little bit less length than A. And then C should be about the same length and again tangent to the path. And this is where if you wanted to get an exact length for arrows B and C, you'd have to do some math at this point. So the picture gives us a general relative ranking of strength, and so we can generally make the arrows the right size. A definitely because it's much closer to the two charges, and right in between them is going to feel both a push from the 1 coulomb and a pull from the -2 is going to be our largest force. If the charge was a -1 coulomb charge that we were putting at points A, B, and C, then each of these arrows will be flipped 180 degrees because it would be going against the field instead of with the field. So to bring everything together, what you should be taking away from this is when you need to draw a force vector, you need to look at two things. You need to look at direction, which is going to be tangent to the field, either with it or against it, depending on if you're putting a positive or a negative charge in. And then you need to look at length, and that'll be determined by the density of the field lines at that point.